Hey guys, Mr. Betts here. In this video, I want to start talking about how we can use the definite integral to explore solving a wider variety of area problems. So if you remember, the definite integral is interpreted as an area, specifically an area between a function and the x-axis. And so we're going to take that idea and we're going to expand it so that we can find areas of different types of regions, not just regions bounded by the x-axis. So let's talk about a few ideas here. First of all, the biggest idea is if we want to find the area of a region bounded above and below by two separate functions. So instead of above by a function and below by the x-axis, say above by f of x and below by g of x, then we can find that area using a definite integral that looks like this right here. And the idea is if we imagine a Riemann sum rectangle, just like the ones that we were using for areas with the x-axis, the height of those rectangles can be found by subtracting y values, and the width is still going to be delta x. So the height, we subtract y values, the width is delta x, and so we can imagine a Riemann sum that would represent an integral that looks like this. So we're still integrating along the x-axis from an x value a to an x value b, and that's going to depend on the area we're trying to find. And we're going to subtract the top function minus the bottom function. So a few notes about that. And the first is the most important thing. When we are finding the area between two functions, we always want to do top minus bottom. The reason we want to do that, we're actually solving area problems here. So we're interpreting an integral as an area. And when we're finding areas, we always want the absolute value of the area. So we always want our height to be positive, and to get a positive height, we want to do the bigger value minus the smaller, or the greater minus the lesser. So we always want to do top minus bottom to find our heights, and that's going to give us our integrand. Note number two, if the functions cross each other, then the top and the bottom functions are going to change. So in that case, if we need to do top minus bottom, we're going to have to split the integral up at a point. And to find the area of one region, we would do top minus bottom, and the area of another region, also top minus bottom. So you can see here that in this particular setup, g of x is on top for the first interval from a to c, and f of x is on top for the interval from c to b. The next note is that it doesn't matter if f of x or g of x or any part of them is above or below the x-axis. As long as we're doing top minus bottom when we're subtracting the functions, then the height is always going to be positive for our Riemann sum rectangles. So you can imagine a few different situations where we have a bigger positive minus a smaller positive gives us that positive height. A positive minus a negative is going to be it's going to end up being a positive plus something, so that's going to give us that height. A smaller negative minus a bigger negative is going to give us a positive height also. So regardless of where the functions are relative to the x-axis, above or below, the top minus the bottom will always give us the positive height of a Riemann sum rectangles and ultimately the area of the region. Fourth note, a lot of the problems that we're going to see are not necessarily going to be given the beginning x value and the ending x value, but we might be told that it's going to be bounded just by two curves where they intersect. So the intersections of those are going to be important. So the intersections are going to give us our lower limit and our upper limit on our integral. So in those cases, we want to set those functions equal to each other. We might have to do that algebraically by hand. We might be able to use a calculator to do that, but we might have to set f of x and g of x equal to each other to find the intersections to use as our limits. And number 5, if the top or the bottom function changes along the interval, we're going to have to split the integral up again. So we saw this when the top and the bottom function cross each other, but it could also be a situation where the top and the bottom just change from one function to another. So the area that's pictured here for this part of the integral, we're going to be using f of x as the top and just the x-axis, y equals 0, which we can think of this right here as f of x minus 0 as top minus bottom. for that part of the integral. And then for this part of the integral here, we have f of x on top and g of x on the bottom. So at that point where we're changing from using the x-axis along the bottom to using g of x along the bottom, we have to split it up into two separate integrals. So this is something where we might have to partition the entire integral into separate integrals, and picturing Riemann sum rectangles to represent these areas can be really useful. So we can picture a Riemann sum rectangle here that doesn't have anything to do with g of x, and then we can picture a Riemann sum rectangle here that's bounded below by g of x. So we can use that to build our integrands here for our intervals. And the last note, if we are doing a problem where we don't know what the graph looks like, then we can determine which function is on top or which one's on the bottom just by plugging in a value on the interval. So we do have to be careful about maybe having intersections along the interval, but if you imagine f of x is, let's say we know f of x is on top and g of x is on the bottom, then if we pick some point on the interval here, some x value, then f of c is going to be greater than g of c. So if we just plug a point in along the interval and see what the value of the function itself is, that will tell us which one is the top function and which one's the bottom function. So if we don't know what the picture looks like, but we know what the interval is, we can pick a point along the interval and see which one's bigger. Whichever the one is the greater one, that's the top one. Whichever one's the lesser one is the bottom one. If the curves do intersect on the interval, which we can figure out when we set g of x equal to f of x and solve this equation, if we have intersections along the interval between our endpoints, then we might have to check which one's on top and bottom on each of the subintervals. So let's say we know g of x and f of x are equal to each other at 3 points along the x-axis, then we need to check which one's on top along the first subinterval and which one's on top along the second subinterval.